Python. My name's Suzanne Cray and I'm the host for this session, and I'm also joined by my colleague Leah Batstone, and she'll be moderating today's session, bringing your questions to today's panel if time allows. During the session, please use the question window on the right-hand side of your screen to ask questions. All attendees are in listen-only mode. If using social media today, the hashtag for the event is hashtag CAS Inspire. And so without further ado, I will introduce the panel for today. This afternoon, I'm delighted to be joined by Pete Ring and Miles Berry. Pete is head of computing at Fulford School in York, where his desk has been invaded by robots and all sorts of semi-disassembled electronics. He's part of the York CAS secondary online community. Thank you. Miles Berry is Principal Lecturer in Computing Education at the University of Roehampton. He serves on CAS's board and was part of the team that drafted the English computing curriculum. So thank you very much both. Obviously, if you have any questions, put them in the window and we will put those to the panel later on. Okay, so I'm going to just pass over to Miles now.
And I'm going to attempt to do the screen share thing. I can't remember. Oh, I see it now. Okay, you've been made a presenter. I say I've been made a presenter. Okay, and share this window. Hopefully folks can see that now. It's such a pleasure to be able to do one of these. It really is. Thank you so much for the invitation, for the opportunity. We've got this brief of STEM links with computing. I often see computing as the silent C in STEM. I think it crosses into science and technology and engineering, and particularly for me as a former mathematician, into mathematics. And it's solving some interesting or vaguely interesting maths problems that I wanted to talk with you about this afternoon. So one of my go-to sources for this is this lovely projecteuler.net website, where you've got like hundreds of really quite sophisticated maths problems. I think this is a great resource for perhaps your more mathematically interested students. This is a really good place to send them to if they finish the exercise that you've set them, if you want to stretch a challenge exercise there. So I thought what we would do for, I don't know, maybe 10 minutes this afternoon is just have a look at a couple of those and see how we might get on solving them. So here on the archives, it starts off relatively gently. The first of these multiples of 3 or 5 solved by nearly 1 million people. They get a lot harder really quite rapidly. I think I've got as far as the 50th, at which point I kind of gave up. Also a really good place for you to go to hone your programming skills, particularly if you're picking up another language here. Let's start at the top though, multiples of 3 and 5. If we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum of these is something or other. Find the sum of all the multiples of 3 or 5 below 1,000. I'm just going to copy that text onto my clipboard here and move over to my chosen development environment of choice, which is Jupyter Notebook. I'm using the free Google Colab version, although I'm very conscious that this is now much harder to use in schools. So let's pop that text in from Project Euler, just so I've got an idea of what I'm working to here. I guess you've all got an idea of how you'd go about solving the problem. How would a typical GCSE student attempt something like this? Well, they might start by thinking of the number that they're looking at here. So let's start by a number. Do we start at 0 or do we start at 1? I guess the Pythonic way is to start with 0. And my total so far is obviously 0. I'm going to go through my list. Let's not go all the way up to 1,000 for now. Come back to that later. So while my number is less than 10, so let's do the ones that we were given, do the following. If my number can be divided by 3, or if my number can be divided by 5 without a remainder, then do something. What do I want to do? I want to add that on to the total. So my total is equal to my total plus whatever that current number is. That seems to be all right. Then we want to move on to the next number. This is the bit I always forget when doing my live coding. So number is number plus another 1. And then at the end of that, we should print out whatever our total so far is. Have a look at the code. I'd love to have that sort of audience participation thing of if you can spot a mistake, tell me where I've gone wrong. I'm going to have to do that for myself. Let's run the code and see what we get. 3, 5, 6 and 9, I make that 8, 14, 14 and 9, sorry, 8, 14, maybe something around the 23 mark. Takes a while for it to power up. The suspense is killing me, really is. 23, good. So then converting it to the question which we were actually asked, notice I tested a small case first. Let's have numbers less than 1,000. And he goes off and tells me the answer, 233,168. How exciting is that? Hopefully some of your more geeky mathematician, computer scientist types would get really quite some sense of satisfaction there. Let's have a look at the next one. I think I've got time for the next one. Oh, the good old Fibonacci sequence. So many applications of this. Again, copying the text here, so I've got that as part of my notebook that I'm building up as I go. Let's type that in, paste that in. Each new term in the Fibonacci sequence, adding up the two previous terms, we get this. Considering the terms of the sequence whose values do not exceed 4 million, where would we get with this? Well, let's have a go at this. So we need the first two terms. A and B are going to be equal to, it says starting with 1 and 2. The total so far is 0, okay, whose value does not exceed 4 million. So whilst the last of those terms is less than 4 million, while B is less than, oh, let's not do 4 million just yet. Let's just start with 100, see whether the thing works or not. Well, it's less than 100, do something. So if B is an even number, so if B divided by 2 gives no remainder, then add B onto the total. So my total is equal to my total plus B. What next? Then we need to work out the next two numbers in the sequence. And I think the easiest way to do that is say A and B, the two terms in my sequence. A becomes the old B, and the new B is A plus B. Fingers crossed. Okay, autocomplete not really working for the win there. I reckon that's going to work. Again, I wish we had the audience participation. Can you spot a mistake there? And then with a little bit of luck, print B at the end of that. So we're looking at just these first few. 2 and 8 gives me 10, and 34 is 44. No other even numbers in that sequence. Let's run that, see what we get there. Ooh, 144. That didn't work as expected. If B is that, what? I'm getting a correction. Huh? Oh, yeah, print the total, not what the last number was. Thank you, Will. It's nice to have some audience here. Thank you.
The deliberate mistake, I'm sure.
Okay, there we go. So we've got that. And we are, of course, asked for up to 4 million. So let's change the 100 there to 1, 2, 3, 4, 5, 6 noughts and see what that does. 4,613,732. At this point, we might just go and have a look at what question number 3 is. What have we got? Largest prime factor. Ooh, this looks interesting. Prime factors of this are these. So let's see how far we can get before my time runs out on this one. So what's your method for this? How are you going to solve something like this? I think the first thing I need to do is to be able to test whether a number is a prime number or not. So I'm going to start building a helper function here. So let's have def is prime for some test number P. And then, oh, how do I test if a number is prime? Well, we've got some special cases. If P is equal to 1, then it's not a prime number. So we return false. False. If P is equal to 2, then it is a prime number. Please. Okay. If P is an even number other than 2, then it's definitely not a prime number. So I've got something going on here about if P percent 2 gives no remainder, then it, oops, forgot the colon, then return false at that point. And then we're into sort of more interesting territory. And I'm going to do lots of sort of test numbers here, up to but not including that. So T is equal, my first test number I'm going to try dividing by is 3. Okay, what do we do now? So T is equal to 3, and while T times T is less than the number that we're testing for, less than or equal to, let's do less than or equal to the number we're testing for, then try dividing by that test number. If P divided by the test number gives no remainder. The test number goes into it. So I return false. Can't be a prime number in those circumstances. Then we try the next test number. No point testing for even numbers. We've already dealt with that with my special case here. So t is 2 more than that, the next odd number there, up to the square root of my original number or something approximating it. T is 2 plus 2, keep doing that. And then if all of those, if that test, if it doesn't go into it for any of those numbers we test by, then we know that we're dealing with another prime number. So I reckon return true at this point. No syntax errors, that's a relief. I want to test it. Is prime, what do you reckon? 101, prime number or not prime number? Let's see what we get. Is prime true? Yes. What about is prime 1001? False. It's not a prime. 7, what is it? 7, 11, 13 goes into 1001. Not a prime number. At this point, I'm afraid my margin is too small to complete the whole solution to finding the largest prime factors of those. But I think starting with a helper function like this gets you a long way along the road to solving this one. So what was that? That was about 10 minutes. And we got through 2.5 of these Project Euler questions. They're really well worth visiting. And I think this is a lovely way of linking some quite interesting, for some values of quite, maths and their Python programming together. Can I hand over now to Pete, please?
Thank you, Miles. Just want to say thank you very much, and I'll pass over to Pete.
So thank you, Miles. Whilst you just get screen sharing sorted, it's fascinating to watch how somebody goes about approaching a solution. When you just see the final thing, you get a solution, but you learn so much more from that live coding process. So it's interesting you went for while loops more than for loops. Why did you go for that approach?
Oh no, people asking me questions.
Yeah.
I reckon that seems to be what the common practice is when it comes to GCSE coding. I know it's not necessarily the Pythonic way, and if we had more time, I'd show you my one-line solution to the first one using list comprehensions. But my friends who are teaching GCSE say, funky Python magic, not mentioned on the spec. You can't do list comprehensions. I mean, there's lovely recursive solutions to Fibonacci, not particularly efficient, but there's so many other ways of solving that. And the Project Euler set really gets you thinking about better ways of solving this. I think the reason why I went for a while loop is I didn't know quite how many terms I'd need, certainly not in that Fibonacci one. I want to stop when I get to the 4 million. I don't know quite how far that's going to take me.
Fab. Thank you. And one other question. You said it was the computing is the silent C for STEM. Would you go for shkatem or kashtem, or how would you like to pronounce it?
A silent C. It doesn't need saying. It's so obviously there.
It's just implicit, running throughout and supporting everything. Absolutely. I like that. So could I just have someone confirm? Can you see on the screen it says aims and introductions? Am I showing the right screen? Yeah, fab.
Yeah, that looks good.
So I think it's fab to have Miles's live coding. I think that's where we want to get our students to, and hopefully some of the things that we go through in my session are some tips on how we can get students to that level of confidence, because I know there's very few students in my GCSE class who could do that even in a quiet environment, let alone under pressure of lots of people watching. So well done. But that's the kind of thing they have to do under exam conditions in some of the GCSEs, and there are some tips to get some students there. So I am hopefully going to talk about how we can build and why we can build some links into STEM with a silent C, some resources that we can play around with to tie in with space, and then where we can get some help and support and resources to build on that, particularly linked to STEM careers. So first of all, why? We all know there is a massive skill shortage in STEM, and it is essential that we raise that with people of every gender and ethnicity and background and ability range. But it's not the only reason. We don't want to just say do computing because it leads to a future job. We want students to do it because they love it. We want students to do it because it's worthwhile in its own right, intrinsically. I think some of the stuff that we're doing today ties in with some of the things that anecdotally I think are the hardest for primary school teachers to do. It's this simulating physical systems. Whenever I work with primary school teachers, that's the bit that they think, well, what does that mean, let alone how on earth do we do it? And at Key Stage 3, that then leads on to evaluating computational abstractions. And when you have a non-specialist delivering Key Stage 3 computing, they look at that phrase and they think, no, thank you, I don't get it. So it's actually really engaging and really fun to teach if we can find some ways to do it. So we'll have a look first of all at this resource. This is the NASA website for the Ingenuity drone. So I love this. There's some amazing resources here, and NASA have made public a lot of their resources that they use to simulate and prepare for the Mars mission. And there's a real buzz in the classroom for students, top-end ability, low-end ability, boys, girls, of thinking the what if, how can Mars impact? I know it's millions of miles away, but actually students can get just so excited about it. Even to the point of, have I got this web page up open here? Oh no, I don't want to log into CNN. Thank you very much. I had to get it ready. There's some new Heinz tomato ketchup, which has been designed in space conditions. So the idea of simulating what it's like on another planet can help us with food design, with product design, with all sorts of industries that aren't just smelly boys sat in a dark room writing code. There's a whole plethora of opportunities for students to get involved in. So I thought, well, how can students write a minimal amount of code that pushes their Python understanding in a way that's quite engaging? I came up with this. This is something that you can play around with. We'll share the resources in the text chat and shared around afterwards. The idea is students can write some code to simulate the Ingenuity drone on Mars. Now the challenge is to get the rotor speeds just right so that this little drone helicopter thing will hover at exactly 2.5 meters. And it's a bit of an introduction into some of the engineering problems that scientists face, because you can't control it like you would a real life drone. I had to renew, I'm rubbish at flying drones, but I had to renew my, is it CAA license or something? I haven't flown my drone since last time I renewed it last year. But if you tried to do manual control on Mars, I don't know how long it would take. I think something like 12 seconds, maybe someone can correct me, to get the radio signal from this planet to another planet if the planets are close to each other. And you just can't have a feedback loop that is reliable enough to control it manually. So it all had to be coded in advance. So some pretty incredible engineering feats by men and women who work in all sorts of different space agencies to make this work. And it was really exciting to watch the achievements of this Ingenuity drone, even more so because it was made with like cheap computing products similar to a Raspberry Pi that you could make in a classroom environment. It's not like the super expensive Mars rover. It's the kind of thing that you could make yourself. So I had some students in year 8 who literally spent hours and hours and hours tweaking this code to say, right, if I want it to get it to 2.5 meters above the ground, well, what's happening here? We've got a countdown here. Don't want to wait for that, thanks very much. I'll spin the rotors up. Maybe I'll spin it up to 80% to begin with and see what happens. So we're getting the drone rotor's speed to go up. It's going up to hopefully 2.5. Oh, what's happened here? So the whole kind of feedback loop that we talk about in engineering, we're overcompensating. Like we've gone above 2.5 meters, so therefore we've switched the rotors off. But because gravity is lower than it is on Earth, it keeps on going up until it slows down, and by that point we switch the rotors off so much it just bounces back on the floor, and it's a real engineering challenge for students to work through. So students can play around with this. It's quite a challenge, or there's a simpler version which I'll share as well. I'll maybe pop that into the text chat if I can work out how in a moment. This one's a little bit easier because we're now iterating through a list. We're saying start with the rotors at 0%, then switch them on to 100%, and then 50, and then 30, and then hopefully it should hover at roughly 2.5 meters. We'll see if this works. Let's just run it again. So you can imagine, would students be able to write this out for themselves from scratch with the kind of confidence and our ability to articulate what's going on that Miles did at the start? I'm not sure if many of my students would. So how do we get to that point? So this led to a kind of collaborative project that I put together with some other teachers in York of how can we support students through lockdown to code regularly, to compete against each other, to build up their confidence little by little. So the Ingenuity drone idea was one of the episodes from live.withcode.uk. It's a free resource that you can try out. I won't put you through watching a video, but it's similar to Miles's live coding. It starts from a blank canvas and builds up the code so that you can see how it works. Students who really struggle, the ones who say, sir, I just don't get it at all, we can drip feed them a little bit of Python syntax by each week just typing out. I find there's usually about 3 or 4 students in each class who understand the concepts, but their typing speed lets them down so much that programming is a frustrating activity for them. Most of them, to be honest, it's the other way around. They can type and it's the programming constructs that confuse them, but for some, they need to become better at touch typing. And then we've got the links to the simulator activity with some challenges underneath. I really like putting some comments in with challenges for students to work through, so they've got the instructions alongside their code. But I really liked the look of the collab resources that Miles showed. This one, this is a K-Pride activity. So we start with the same code from the challenge, the same Ingenuity drone controls, but this time it's code comprehension. It's saying, where in this code can we see an arithmetic operator? It's kind of the activity that students would have in an exam. So we see there's one, there's a minus symbol. Are there any others in here? No, that's the only one. Is there a string in here? Have we got any text? Yeah, here we go. And if they get it wrong, you can have an attempt, and then if you get it wrong, you can click the show me button. This builds on Sue Sentence's absolutely phenomenal work on Prim. The extra addition from Prim, as in predict, run, investigate, modify, make, is debug, which is part of the investigate, but it's the one that I think instills the most fear in both teachers. Help, I've got a sea of hands, I don't know how to debug these. Or for students, my code's broken, I don't know what to do next. So again, it starts with the same code and it's sabotaged, and you can sabotage it again as much as you like. So teachers and students said what the most common mistakes are in Python codes: incorrect capitalization, incorrect comparative operators, the wrong use of brackets, that kind of thing. And it'll inject those into your code so that you can attempt to debug it yourself. So that's some simple Python activities that you can do to bring space into the classroom. If we come back to this, I think it's really exciting to get students to dream about what we're doing in the classroom now, how that can impact on the world, how it can change and influence and transform society, both now and for their futures. So I'd really recommend, if you haven't already explored the STEM resources, I think I've got this open somewhere. Let's see. So the first link on that slide is resources for schools and for colleges. If we go secondary, and then we've got explicit resources for computing, but also ones for careers in space. And I love this one because you've got some really good profiles of some phenomenal influential role models of a variety of different ethnicities and genders who we can just celebrate in our classrooms, so that when students walk into a computing lesson, they know this is about me, this is about someone like me, and there's an outlet for something I'm passionate about in what we're doing today. So that's really as far as I wanted to go today. I'll pop into the text chat the link for the Python activities. You can try and make that little Ingenuity drone hover at 2.5 meters. I think the record for the amount of time somebody took on it, he logged about 30 hours to try and get it to work, which was extreme commitment. So dead impressed with that. Yeah, and then I'll hand over to any questions if that's okay.
Thank you very much, Pete. Just so that everybody knows that's watching, Miles has had to step out for another meeting, but he will pick up on any questions if they're not answered in this session. Leah, are there any questions for Pete?
Hi. So we had one question come through earlier. So I think it was mainly aimed at Miles, but hopefully, Pete, you'll be able to help. So the question was, what site are the program challenges on which Miles was demonstrating?
Okay, yeah, that's a really good site. It's Project Euler, and you can solve the challenges in any any programming language. So they're set up so that you can do it in Excel if you want. You can do it on paper. Sometimes students try and brute force it to write a program that tries to go through all the possible combinations, but especially once you get beyond the first 5 or so, that's very computationally difficult to do. You have to write a solution, but you can do that in Python, you can do it in C#. So I find it's a bit too much for most GCSE students, but I tend to find a bit of independent work for A-level classes. I just set, a weekly homework task where they have to choose one of the Project Euler challenges and they have to attempt it. They don't necessarily have to solve it because some of them are hard, but they have to attempt it, and then they submit the code to me of what they've done so far, and we'll have a little discussion for each week of 1 or 2 solutions. So projecteuler.net, I'll see if I can post that into the text chat now. Great question.
Thank you. Leah, is there anything else?
Thank you. No, that's everything from me. If anyone does have any follow-up questions, if you just go onto Compact School, you will be able to find our email address, and I'll make sure that gets sent through to the correct presenter after the session.
Thank you, Leah. Okay, thanks again to Pete and to Miles for joining us today and for speaking. It's been a fascinating session. It's got my brain going, I must admit. It's really, really good. Thank you. And thanks to everyone for joining us today. Please do encourage any highlights from today's session via social media using that CAS Inspire hashtag that I mentioned earlier, and on the CAS website as well. And obviously, if you've got any questions, pop them on there too. At the end of this webinar, a short survey will appear on screen, and we'd be grateful if you could take a minute to complete that survey. Please continue to spread the word about CAS Inspire. We are hosting further CAS Inspire sessions all the way through into 2022. Some really exciting stuff coming up. Next Wednesday at 4 o'clock for our secondary CAS Inspire session, we've got Computing for All. How can we improve outcomes for learners from different socio-economic backgrounds? Join us next week to find out more. So thanks again, thanks to our presenters, thanks to Leah for monitoring the questions, and we hope to see you next time. Bye for now.
Thank you, bye-bye.